I welcome you to this channel once again, and I want to sincerely thank as many of you out there that have subscribed to this channel. Now, in these lessons today, we are going to be looking at the terms that are used in describing a simple harmonic motion. They are displacement, amplitude, period, frequency, and add velocity to it. I've been talking about oscillatory motion for some time now, the motion of a body to and from motion of a body about a fixed point, and I've gone far in that lesson. So if you are just joining me now, please, I want to refer you to my previous video lessons so that you can be on the same page with us. So today we are looking at displacement. Let's start with that. We say displacement is the body's position relative to the center of oscillation or fixed point. This is measured in meters. And then we can show that the variation of the displacement of a bulb in simple harmonic motion of a body can be represented graphically using a sine or cosine graph. Let me show you. If you look at this diagram, I have a pendulum bulb here that is fixed at a point here. Let's call that point O, and then suspended from that point. And then this is also the center of oscillation. This reference point here, we call that the fixed point or the center of oscillation. Now, if that is the starting point, I can give this my bulb a slight push in the towards the right. That is, if it moves like that, like this, and then up to point A. Let's say point A is the extreme point this bulb gets to before it, falls back or swings back to the same reference point or center of oscillation. So you can see that at this point O, the displacement of the bulb is zero. So I come in here, on my displacement time graph already drawn here, I'll mark this point, means that is the time t is equal to 0. The bulb was at the center of oscillation as its rest point. Now, as it goes from point O to point A, we can describe that using, from this graph, this point represents point A, because between point O and point A, we call that the amplitude of oscillation. That's the maximum displacement. So from there, the bulb returns from A back to O, represented by this portion of the graph. This is it, back to point O here. So this is the point O. Then this body is not going to stop at point O because of the body's inertia. It goes past point O towards point B, and we can show that like this on our displacement time graph. This is the journey of the bulb towards point B, reaching point B at another extreme. Okay, that's called that point B. And then after point B doesn't stay there, it swings back to point O. So the motion continues like that until it gets back to point O at this point. So you can see clearly here that the displacement time graph of this body can be represented using a sine graph. This is sinusoidal graph, or simply call it a sine graph. Similarly, you can use a cosine graph to represent the displacement time graph of this body. How do we achieve that? In that sense, we are going to, start the displacement, let's say from point A. First of all, displace the bulb, move it to a point A, and before I release it. At point A, the body is already having a maximum displacement. Okay, that is represented by this portion of the graph. It's already at its maximum displacement. I want to release the ball at point, because at point A, that's the starting point now, and t is equal to 0. So when I release the bulb at point A, okay, that's it there, it swings to point O where the displacement is 0, and that follows this path to point O here where the displacement is 0. And it continues to point B, so the graph continues like that to point B, another point where the displacement is maximum. All right, so it goes like that back to point O and then finally to point A. So when the displacement started at point O, we can use a cosine graph. This is a cosine graph to represent the displacement, the variation of the body displacement and time, or versus time. But when the displacement starts, or the oscillation starts from the origin, then we can use the sine graph to represent the displacement time graph of the body. All right, so this is how we can use that. Now the next one there is the amplitude of oscillation. Amplitude is defined as the maximum displacement to the body from the mean position, from the rest position, or from the equilibrium position. So we can still come back to the previous graph I showed you here, and that's the displacement time graph. From here, we can determine the amplitude. Remember, it is a maximum displacement, and this time as is always taken as our reference position, as our minimum, so as our equilibrium position. So the displacement from this x-axis up to point A, of course, in waves, we call this point A the crest of the graph, the crest or the peak. Okay, so the distance measured from this timeline to this peak on the graph is called the amplitude, and that is measured along the vertical axis. So whatever it is here, if this my axis or graph was graduated, let's say this is 2 cm, this is 4 cm, this is 5 cm, it therefore means that the amplitude x naught is given, is 5 centimeters from this displacement time graph. And we have symbols that we can use to denote the amplitude. We can use x naught, we can use the uppercase letter A, or sometimes we can even use the lowercase letter a to denote or to represent the amplitude of oscillation. And sometimes equations like this can be given since we are talking about representing displacement time graph using sine graph. An equation for sine graph is this: x equals x naught sine omega t. So which means this my x naught is called the amplitude of oscillation. Because for an example, you'll be given a question like this, that a simple pendulum or thereabout oscillates in simple harmonic motion, and this is how the displacement varies with time. X is equal to, they may say, 15 sine 200 pi t, something like this will be given to you, and they say from this graph determine the amplitude of oscillation. So you just simply compare these two equations. For this equation, what is the amplitude? And if x is given in centimeters, then you know that the amplitude of oscillation x naught is simply 15, it's just 15 centimeters. That is the case where they give an equation that relates displacement and time. From that equation, you can determine the amplitude of oscillation. Okay, quickly let's move to the next term that is used in describing simple harmonic motion, and that's the period of oscillation. We say here it is the time taken to complete one oscillation or one cycle, the total time taken to complete one cycle or one oscillation. And for a pendulum motion, I've been using the case of pendulum, can also apply to other systems in simple harmonic motion. If a bulb starts oscillating at the center of oscillation here, which is point O, let's say that's the starting point, and it's giving a slight push. This ball leaves this point O, first of all to point A like this, reaching point A, which is the extreme point, the highest point it rises to, before it starts swinging back to point O. It goes like this, and then it goes past this point and then back to point B. This complete one cycle. This is one cycle. So the total time taken to complete this journey, this path, starting from point O to point A, back to point O to point B, and then to point O, that's complete one cycle. So the time taken for that is called the period T of oscillation. Of course, we use the uppercase letter T to represent the period of oscillation. So if the time taken to go, for instance, from point O to point A is 2 seconds, time taken for this bulb to rise from O to point A is 2 seconds. They may ask you to calculate the period of oscillation. From here to here is one part of the journey, from here to here is another, from here to here is another, and finally from point B to point O is another. Okay, like dividing the entire circle into 4 equal parts. So which means if you have that right like this, it means the journey from point O to point A is just a quarter of a circle. So it takes a quarter, 2 seconds to complete a quarter of the journey. So which means I need 2 seconds again to complete, to go from O to B, and then from B back to O, and from O back to A, and so on and so forth. So total time taken will be 4 seconds. This is 2 seconds, 2 seconds, 2 seconds, 2 seconds. That is 4 times 2, sorry. Total time taken is going to be 8 seconds. That gives the period of oscillation, because sometimes we ask to find the period. If it takes 2 seconds to go from point O to point A, what is the period? That is what we have just found here. Again, you may be asked to find period of oscillation from the displacement time graph, like you can see on this on my paper here, that how do you determine the period? Period, we say, is time taken to complete one cycle. If I'm sure that this is the starting point, the center of oscillation, it means that from here to this point here forms one period T. So whatever time it is there, according to the graduations or the divisions or the time axis, I should be able to find the period of oscillation. So if this was given like this, let's say for instance, this is subdivided into the divisions. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and let's say this time here is let's say 0.2 seconds, 0.2, 0.4, 0.6, 0.8. So which means the period of oscillation is 0.8. After 0.8, I can have my 1.0 and so on. We can also determine period by taking the crest to the next adjacent crest. Time interval between this crest and this crest also forms the period. And this time now is 1.0 second, you know. Then 1.0 second minus 0.2 still gives you 0.8 seconds, which is the period of oscillation. So you'll be able to find the smallest division and then use that to determine the period, knowing that the period is one complete cycle. And one complete cycle consists of two half cycles. This is a half cycle, and this is another half cycle. We can also express period as time taken t to complete n number of oscillations, and that this n is an integer, it's not a fractional number. So the time taken t is given in seconds. Of course, that's the unit of period. N has no unit. N must be an integer. Okay, so we may need to take one question to see how that equation is used. Look at this question. The question says that a pendulum completes 50 oscillations in 1 minute. You have to calculate its period. Period is given by t divided by n. And since it completes 50 oscillations in 1 minute, 1 minute is 60 seconds. You have to change that minute to seconds divided by 50. So that gives you 1.2 seconds. Okay, you can see that now. That gives the period of oscillation of the body. Okay, maybe I'll take another question again on how to, now period, the time taken, time interval taken, the time intervals taken to complete 20 oscillations are recorded as follows. You see 45.5 seconds, 45.4 seconds, and 45.7 seconds. They calculate the mean period of oscillation. Now, before we can find the mean period, we have to first of all calculate the mean time. The mean time or the average time is given by, just finding the average of these three times. This plus 45.4 plus 45.7, now divided by 3 because there are three different times, you know, given for the oscillation of the body. So I need to refer to my calculator here. I have 45.5 plus 45.4, then plus 45.7. Okay, that gives me 136.6 divided by 3. So if I divide that by 3, it gives me 45 so my main period approximately 45.53 seconds. So let me take it as 5 seconds. So that's the mean time. Then my mean period is going to be mean time over number of oscillations. That gives me 45.5 seconds divided by 20 because there were 20 oscillations. Time taken to complete 20 oscillations. So if I divide that by 20, I have my final answer, which is 2.27 seconds approximately, or thereabout. So that gives me the mean period of oscillation. I don't want to stop here. Let me quickly look at the next parameter, next 10, used in describing simple harmonic motion. That is frequency. What is frequency? It is the number of oscillations or cycles completed in a unit time or per unit time. Now, don't make the mistake of saying that it is number of oscillations completed per second. Students always make that mistake. You don't say per second. It is per unit time because second is not a physical quantity, it's a unit. You must define a physical quantity with respect to another physical quantity. But we must define our unit time. In this topic, our unit time is taken as a second, which is the SI unit of time. All right, so this is a mathematical expression of frequency. Frequency is n over t, where n must be an integer and time is the second. So the derived unit of frequency is a second raised to power minus 1, that is per second, which is equal to equivalent to the hertz. That's the SI unit of frequency, which means a frequency of 1 per second is the same thing as a frequency of 1 hertz. So if a body in simple harmonic motion completes, let's say, 10 hertz or moves with a frequency of 10 Hz, or it's oscillating with a frequency of 10 Hz, it means that it's completing 10 oscillations, 10 oscillations per second. That is the interpretation of frequency of 10 Hz. Now look at this question. A body completes 50 oscillations in 1 minute. What is its frequency? Its frequency is number of oscillations divided by time. That gives you 50 divided by 60. I think when you divide this, it gives you 0.83 Hz, not even up to 1 Hz. So that is the frequency of oscillation of this body. And we can also express frequency just like period too, as frequency is also given as 2 pi omega rather, divided by 2 pi. If you are given the angular frequency, divide by 2 pi, that gives the frequency of oscillation. And therefore, period 2 is 2 pi divided by omega. This is used when you are given the angular frequency. You divide the 2 pi by that, that gives you the period of oscillation. And we can also show that there's a relationship between period and frequency. How are they related? Frequency and period. Because if you come back here now, the period already define it as t over n, time taken to complete a number of oscillations, and then frequency is n over t. I want to show there's a relationship between period and frequency. I multiply the two equations. I have Tf equals to t over n times n over t. That's multiply this equation by this equation. I have that. So that if you check up now, this will cancel out this, t cancels t. So the product of frequency and period is equal to 1. Or you can write, if I need to find a period, that gives me 1 over frequency. Or my frequency is 1 over period. So this gives the relationship between frequency and period. So in simple harmonic motion, you are given, or there's a way the equation is set, maybe from a displacement time graph, which you can easily evaluate your period. You get that period, you can reciprocate it to get the frequency of oscillation. Now, finally, let's look at the last term here. That is the velocity of a body in simple harmonic motion. Of course, you know what velocity is, or speed, distance over time, or displacement over time. Now, this is the expression, the equation we can use in calculating the velocity of a body in a simple harmonic motion, and is given with respect to amplitude and displacement. And this is amplitude squared minus displacement squared. This is more like difference of two squares. It's not x naught minus x squared or x all squared. Okay, so don't make that mistake of thinking it's so. Now here, quickly come back to this my graph. We want to show point. Let's see, given these 3 points, these two extreme points, and then the center of oscillation point 2. At what point will the velocity be maximum or be 0? Now at point A or B, the displacement is equal to the amplitude, because when the body rises to such a point, from here to here, of course, if this is the highest point it reaches before it comes back to point O, then we can measure our amplitude between point O, which is our reference point, to point B on either side. Even from here to here too can also be used to determine our amplitude of oscillation. Okay, so when the ball is at point A or B, our displacement is this. So when I slot it into that equation, I have this is equal to x naught squared minus x naught squared. That gives me 0. So so that whatever you multiply by 0 gives you what? 0. So at either end, A or B, the body's velocity or speed is 0. The speed is what? 0. So which when the body comes to rest momentarily at point A or B. Now let's see at the center of oscillation, x naught is equal to 0. Sorry, displacement x equals 0 at the center of oscillation. So what's my speed of velocity? Is omega multiplied by x naught, square root of x naught squared minus 0, which gives me v is equal to omega times square root of x naught squared. X naught squared is x naught, so my velocity becomes omega times x naught. Okay, and that is the maximum velocity, and that takes place at the center of oscillation. Velocity is what? Maximum. So which means that at any other instantaneous position between point O and point B, because the bulb can be any of these positions or can be at any of these points I marked here. Let's say at this point the bulb is at a distance of 2 centimeters, for instance, from the center of oscillation. Then we can find, given that the amplitude from measure from here to here is 5 cm, that is my x naught. Therefore, I can find the if I know that my omega is 2, I can find the speed at 2 cm from the center. That gives me 0.05 squared, converting centimeters to meter, minus 0.02 squared. Then I can find the instantaneous velocity when the bulb is, let's say, 2 centimeters from the center of oscillation. The same thing can apply if the bulb is around here. The same equation is used to find the velocity of the body. All right, next video we shall see more examples on this, that deals with terms that are used in describing simple harmonic motion.